I'm going to walk through an illustration of using the parallel axis theorem. So imagine that we're given two thin bars of mass m and length L, like so. In the top case, the rotation axis is right through the center of mass, which, for a uniform density bar, will be right through the middle of the bar. In the lower case, let's say that the rotation axis is located 1/4 of the way down the bar, like so. Now in class, I went through and did an integral to demonstrate that the top case has a moment of inertia of 1/12 ml squared. In the lower case, the rotation axis must be located a distance L/4 away from its center of mass, right? Because the rotation axis was located L/4 from one of the sides, it's another L/4 to get to the center of mass, so that distance is the length divided by 4. And in class, I had students do that integral. Coincidentally, it was the tougher integral that I had the students do. And you should have found that the moment of inertia for that case was 7/48 ml squared. So what I want to show you now is how we could have used the parallel axis theorem to get that second moment of inertia much more quickly just from knowing the first. The parallel axis theorem says that the moment of inertia through some parallel rotation axis is equal to the moment of inertia through the center of mass plus the mass of the object times the distance squared, where the distance is the distance of the rotation axis from the center of mass. Let me show you how it works. So in this case, we'll identify I1, that moment of inertia, with the moment of inertia through the center of mass, and as I said, that's 1/12 ml squared. The second moment of inertia we'll label I parallel, and now we can apply the parallel axis theorem, like so, and I can immediately substitute in I1 and I2. Okay. Now we need to identify an expression for d. Well, as I said, d is the distance between the rotation axis of interest and the location of the center of mass. In this case, that's just L/4. And the nice thing is you don't even need to worry about the sign of this because it's getting squared. So we can just choose d equals L/4, that'll be fine. Plug that into our expression in the parallel axis theorem. Okay, now we can go in and substitute in the expression for I1 and simplify that term on the right a little bit. So we get that I2 equals 1/12 ml squared plus 1/16 ml squared. We can pull out a factor of ml squared, and now we just need to find a common denominator between those two fractions. We do that, and we get that I2 equals ml squared times 7/48, and recover the expression that we have over there on the left, I2 equals 7/48 ml squared. In my opinion, much easier to apply the parallel axis theorem than to set up and solve another integral. All you really need is to know one moment of inertia through a rotation axis, and you'll automatically, using the parallel axis theorem, be able to get any other moment of inertia as long as the rotation axes are parallel. Now, for an irregularly shaped object, you have to be careful. If you chose a rotation axis that was perpendicular to the one you have, you can't apply the parallel axis theorem. You need to make sure, as the name suggests, that the two axes are parallel to one another.